Today in this video lecture we will see chapter 5 principal stresses and strains, and topic is members subjected to normal stresses in two mutually perpendicular directions. The sigma x and sigma y are normal stresses, and this sigma x and sigma y are two mutually perpendicular directions. This is a rectangular bar ABCD of uniform cross sectional area A and unit thickness. This angle is theta. Let the bar subjected to two tensile stresses mutually perpendicular to each other. This sigma x and sigma y both are mutually perpendicular to each other. Sigma x is tensile stress in x direction on face BC. This sigma x is tensile stress in x direction on face BC, and sigma y is tensile stress in y direction on face EC. This is EC. Sigma y is acting on EC. Horizontal force on face BC. This face BC, horizontal force, is equal to stress on BC into area. Here stress is nothing but the load upon area, and horizontal force on face BC, that means this P is equal to stress into area. Therefore P is equal to stress into area. So horizontal force on face BC is P, denoted as Px, is equal to stress on BC into area, and stress on BC is denoted as this sigma x, and area is BC into unit thickness 1. So Px is equal to sigma x into BC into 1. This BE is this plane BE. This is plane BE, and this horizontal stress is sigma x cos theta, and tangential stress is acting along the plane BE, this sigma T1 and this sigma T2. And resolve this sigma x cos of theta into x component and y component. So we get this sigma n2, sigma n1, and this tangential stresses, and this sigma y sin theta is this stress on CD or EC. Vertical force on face EC is equal to stress on EC into area. Vertical force on EC is denoted as Py, is equal to stress on EC is sigma y. Here, see, stress on EC is this sigma y, and area is EC into 1. So from figure 1, sin theta is equal to EC upon BE. See this figure 1. Theta is equal to, sin theta is equal to opposite side upon hypotenuse. Opposite side is EC and hypotenuse is this EB. So EC upon EB or BE, and cos of theta is equal to opposite side this EC upon, no, cos of theta is adjacent side upon hypotenuse. Adjacent side is this BC and hypotenuse is this EB. BC upon EB. BC upon EB. EB or BE. Same. So horizontal stress on face BE is equal to horizontal force upon cross sectional area on face BE. Stress is equal to load upon area. So here load is horizontal force and cross sectional area of face BE. Horizontal force on BE is this sigma x into BC. So this sigma x into BC, and cross sectional area of face BE is BE into 1, unit thickness 1, BE into 1. So sigma x BC as it is upon BE. BE is nothing but the, see here BE is equal to BC upon cos of theta. BC upon cos of theta. So horizontal stress on face BE is equal to sigma x cos theta, and denote is at equation 1. Use this cos theta for B because we have to cancel this BC, upper side BC, this BC, this BC, this BC get cancelled. So that's why I use this equation by seeing this BC. Next is vertical stress on face BE is equal to vertical force upon cross sectional area on face BE. So vertical force is this sigma y EC into 1, vertical force on EC. So sigma y EC upon cross sectional area of BE is BE into unit thickness 1. So sigma y EC as it is, BE is, see this, we have to cancel this EC, this EC and this EC. So by seeing this EC, we use this B is equal to EC upon sin theta, EC upon sin theta. So vertical stress on face BE is equal to sigma y sin theta. So resolving stresses into two components, one along the plane BE and other to the plane, other perpendicular to the BE as shown in the figure. So this sigma y sin theta and sigma x cos theta. Sigma y sin theta is this vertical stress on face BE, and sigma x cos theta is horizontal stress on face BE. So this sigma x cos theta and sigma y cos theta. Sigma x cos theta is horizontal stress on face BE, and sigma y sin theta is this vertical stress on face BE. And resolve these stresses in this x direction and y direction. So stress perpendicular or normal to plane B is equal to, see this figure, stress perpendicular or normal to plane B is this sigma n1 and this sigma n2. Therefore the sigma n is equal to sigma n1 plus sigma n2, and sigma n1 is nothing but, see here, this sigma n1 is equal to sine of 90 minus theta is equal to opposite side upon hypotenuse. Opposite side is the sigma n1 upon hypotenuse is sigma x cos of theta. So sigma n1 is equal to sigma, see here, sine of 90 minus theta is equal to opposite side sigma n1 upon hypotenuse is sigma x cos of theta. Therefore sigma n1 is equal to sine of 90 minus theta and multiply by sigma x cos of theta, and sigma stress, normal stress 2 is equal to opposite side upon hypotenuse, that means sigma n2 upon sigma y sin theta, and here this angle is theta, so sin theta is equal to opposite side upon hypotenuse. Opposite side is sigma n2 and hypotenuse is sigma y sin theta. So sin theta is equal to sigma n2 upon, this is sigma y sin theta. So sigma n2 is equal to sigma y sin theta multiplied by sin theta. Yes. And by solving it mathematically, sigma x cos theta, this sin 90 minus theta is cos theta, and this as it is. So sigma n is equal to sigma x cos square theta plus sigma y sin square theta. This cos square theta is nothing but the 1 plus cos 2 theta upon 2, and this sin square theta is equal to 1 minus cos 2 theta upon 2. By solving it mathematically, we will get this sigma n is equal to sigma x plus sigma y upon 2 plus in bracket sigma x minus sigma y upon 2 into cos of 2 theta. This and this equation take common, and this cos 2 theta take common. So next is stress along the plane BE, that means tangential to the plane. So this plane BE, tangential stresses are sigma T1 and sigma T2. So this sigma T1 plus sigma T2, sigma T1 is equal to, see this figure, use opposite side upon adjacent side for tan formula, opposite side upon adjacent side, tan 90 minus theta is equal to sigma n1 upon sigma T1. Therefore sigma T1 is equal to, sorry, here use cos formula, cos theta is equal to opposite side upon adjacent side upon hypotenuse, sigma T1 upon sigma x cos of theta. So here sigma t is equal to sigma T1 plus sigma T2. Here don't use plus because both are in opposite direction. Use minus sign because see this sigma T1 is in opposite direction to this sigma T2. So sigma T1 is equal to cos 90 minus theta is equal to opposite side upon adjacent side. Therefore this sigma T1 is equal to, somewhere something is wrong, cos 90 minus theta is adjacent side upon hypotenuse and adjacent side is sigma T1. So see this cos 90 minus theta is equal to adjacent side sigma T1 upon hypotenuse is this sigma x cos theta. So this sigma T1 we get cos 90 minus theta into sigma x cos of theta, cos 90 minus theta into sigma x cos of theta, and tangential stress 2 is equal to cos of theta is equal to adjacent side upon hypotenuse. Adjacent side is sigma T2 upon hypotenuse is sigma y sin theta. So this sigma T2 is equal to cos of theta into sigma y sin of theta, cos of theta into sigma y sin of theta. Cos 90 minus theta is sin theta, and this all are as it is. Therefore this sin theta into cos theta and this sin theta into cos theta take common, sigma x minus sigma y into sin theta into cos theta. Therefore this sin theta into cos theta divide and multiply it by 2. Therefore tangential stress equation is sigma t is equal to sigma x minus sigma y upon 2 into sin of 2 theta, and normal stress equation is sigma x plus sigma y upon 2 is plus sigma x minus sigma y upon 2 into cos of 2 theta. Resultant stress on plane BE sigma r is equal to under root of sigma n square plus sigma t square, and angle of obliquity phi is equal to tan inverse of sigma t upon sigma n. So maximum shear stress, our tangential stress is this sigma x minus sigma y upon 2 into sin of 2 theta. Sigma t is equal to sigma x minus sigma y upon 2 into sin of 2 theta. The shear stress will be maximum when sin 2 theta will be 1. Sin 2 theta is equal to 1, 2 theta is equal to sin inverse of 1. Sin inverse of 1 is nothing but 90 degree or 270 degree. Therefore, sin 90 is 1. Therefore, maximum tangential shear stress is sigma x minus sigma y upon 2. The maximum shear stress are acting on the plane inclined at 45 degree or 135 degree with the normal cross section. That means this angle is for maximum shear stress required angle is 45 degree or 135 degree with the normal cross section. And maximum and the shear stress and tangential shear stress are similar term. Therefore, maximum shear stress is equal to sigma x minus sigma y upon 2. Normal stress on the plane of maximum shear. Plane of maximum shear, that means theta is 45 degree or 135 degree. See this theta here. Theta is equal to 90 divided by 2, that means 45 degree, or 270 degree divided by 2, that means 135 degree. This cos 2 theta sigma n. This equation is as it is. Equation 3 becomes here. Put here 45 degree. Cos 2 into 45, that means cos 90 is 0. So only this term remaining. Sigma n is equal to sigma x plus sigma y upon 2. And principal planes and stresses. Again, this equation 3 becomes normal stress sigma n is maximum when cos 2 theta is equal to 1, and cos 2 theta is equal to cos inverse of 1, 2 theta is equal to 0, so theta is equal to 0 degree. That means theta 0, that means see, what is theta? Theta is angle between this cross section and to this inclined plane BC. If this theta gets 0, that means only remaining this is on plane BC. So this theta is from like this, theta from here to here. So if this theta is 0, this on plane BC, this is on plane BC. So on face BC, maximum principal stress is equal to maximum normal stress. Therefore, cos 0 is 1. That means, and by solving it mathematically, sigma n is equal to sigma x. This stresses acts on plane AD and BC. This AD and BC. Sigma n is equal to sigma x. When sigma n is equal to sigma x, when theta is equal to 0 degree, that means maximum principal stress or maximum normal stress is equal to sigma x. And normal stress sigma n is minimum when cos 2 theta is equal to minus 1, 2 theta is equal to cos inverse of minus 1, 2 theta is equal to cos inverse of minus 1, that means 180 degree. So theta is equal to 90 degree. That means sigma n is minimum when theta is equal to 90 degree. And theta 90 degree, that means this is on face BC. Sigma is here, theta is here on face AB. So minor principal stress is equal to minimum normal stress. Put this cos 2 theta is equal to minus 1 here. So by solving it, sigma n is equal to sigma y. This stresses acts on the plane AB and CD. When sigma n is equal to minus 5, when there is angle is 90 degree. And when angle is 90 degree, there are minimum normal stresses or minor principal stress. So see angle, when angle is 90 degree, that means on face AB, minimum normal stress is developed, and minimum normal stress, that means minor principal stress, sigma n is equal to sigma y. And when theta is equal to 0 degree, that means on face BC, then there maximum normal stress develop. Maximum normal stress, that means maximum principal stress, and then sigma n is equal to sigma x. And when for tangential stress, when tangential stress is maximum, when theta is equal to 45 degree or 135 degree. See here, theta is equal to 45 degree and 135 degree, and formula for maximum tangential stress is sigma x minus sigma y upon 2. And normal stresses on the maximum shear, that means when theta is equal to 45 degree and theta or 135 degree, then normal stress is also sigma x plus sigma y upon 2. Only sign change between them. So this angle of obliquity is denoted as phi. Phi is equal to tan inverse of sigma t upon sigma n. And resultant stress is denoted as sigma r. Sigma r is equal to square root of sigma n square plus sigma t square. Formula for normal stress is sigma x plus sigma y upon 2 plus sigma x minus sigma y upon 2 into cos of 2 theta. And formula for tangential stress is this sigma x minus sigma y upon 2 multiplied by sine of 2 theta. In tangential stress, sine term is developed, and in normal stress, cos term is developed. So this is methodology of deriving this derivation, member subjected to normal stresses in two mutually perpendicular directions. Horizontal stress on face BE is, this is face BE, horizontal stress is sigma x cos theta, and vertical stress on face BE is sigma y sin theta, sigma x cos theta and sigma y sin theta. Sigma n is equal to sigma x plus sigma y upon 2 plus sigma x minus sigma y upon 2 cos of 2 theta, and sigma t is equal to sigma x minus sigma y upon 2 into sin of 2 theta. Maximum shear stress when theta is equal to 45 degree or 135 degree, and maximum shear stress or tangential stress is sigma x minus sigma y upon 2. This sin 2 theta term remove when there is maximum tangential stress. When theta is equal to 45 degree or 135 degree, then normal stress is given as sigma n is equal to sigma x plus sigma y upon 2. Then this cos 2 theta term is 0. And when theta is equal to 0 degree, that means on face BC, then maximum normal stress develop. Maximum normal stress develop, that means this BC plane is maximum principal plane, and then sigma n is equal to sigma x, and the stresses acts on the plane AD and BC. And when theta is equal to 90 degree, then that means on face AB, minor normal stress then occurs when theta is equal to 90 degree, and minor normal stress, that means minor principal plane, sigma n is equal to sigma y. The stresses acts on plane AB and CD. So this way our derivation completes. Thank you very much.